Hello everyone. Now we will continue our learning on simple reservoir simulation, and we will do the simulation using MBAL software. All right. And our case today will be about transmissibility between two reservoirs. Okay. So I will have reservoir 1 and reservoir 2, and then they are connected, and I will connect them with something that is called transmissibility. Okay. You will know it better, you will understand it better as I will show you. Okay, we are now inside the MBAL. Okay, we start, go to tool, material balance, and then go to options, reservoir fluid oil, tank model multi-tanks. I will have 2 tanks in this case, and then PVT model simple PVT, production history by tank, and no compositional model. As usual, you can provide user information in here. Okay, now we go to done and PVT, fluid properties. We will provide the fluid properties, and then you can follow me. Formation GOR 500 SCF per STB with oil gravity of 39 API, gas gravity of 0.798, and then for H2S 0, no carbon dioxide, no nitrogen, and water salinity 0, for example, fresh water. Okay, and then I will do PVT matching. Okay, but I only have, unfortunately, one data. Okay, that's our limitation in this example. So the temperature 250 degrees Fahrenheit with the bubble point pressure. Here the unit is in PSIA. I will choose PSIG. Okay, so I will close, click done here, go to units, go to pressure. Okay, pressure here, you can see the unit is in PSIA, absolute PSI. I will change to PSIG. So PSI gauge. Okay, so I will click OK, go back to PVT, and then match. Okay, the temperature again 250 degrees Fahrenheit with bubble point pressure of 2200, and one data at reservoir pressure, the gas oil ratio is 500, oil formation volume factor is 1.32, and oil viscosity of 0.4. Okay, with only this data I will do PVT matching. So let's see, click match, press calculate. Okay, and then I will check for the quality of the matching. Go to match parameters, and just a quick review, you can see based on parameter 2, Glasso equation is the best. Parameter 2 for Glasso is 5, but for standing 71, Lassater 200, Vasquez-Beck minus 140, Petrosky minus 45. Yeah, you can see based on parameter 2, the Glasso is the best. Okay, so I will select Glasso. Yeah, although for Glasso the standard deviation is it's not it's not that good. But again, for parameter 1, Glasso is the best. It is closest to 1. 1.00, standing 1.03, Lasseter 1.15, Vasquez-Beck 0.94, Petrosky 0.98. Yeah, so the closest to 1 is Glasso. Okay? And then for the oil viscosity, you can see that, let's check. I think Beck's et al. Is the best. Okay? Beck's et al. Is the best, closest to 1, parameter 1, and for parameter 2, closest to 0. This one, this Beck's et al. And with standard deviation, small, minus 10. Okay? So you can compare with other correlations. And now we can plot. All right, click plot, match data, temperature. I want to show the oil formation volume factor, only 1 point. Okay, we only have 1 point. And now let's check the Glasso. Click the Glasso and then oil formation volume factor. Okay. Where is our point? Oil formation volume factor, I think. Please be careful. Yeah, oil formation volume factor 1.32. Okay, that's right. And then for the oil viscosity 0.4, I think it's okay. Go back to match parameters. Okay, plot oil formation volume factor, and then for Glasso oil formation volume factor. From here, I'm not so sure. Or here. All right, I think, oh, let's do this. Show the Glasso first. Okay, this is for Glasso correlation. And then for the real data, there. Okay, so it's almost perfectly matched. They are very close, right? Very, very close. And then I want to show the oil viscosity, but it's from, no, gas oil ratio instead. Gas oil ratio like this. And then the laboratory data there. Almost perfect match. Okay, or perfect match. So I think it's good. And again, the viscosity for oil viscosity, Bex et al. Is the best. So for example, here, standing Bex, because the viscosity will use Bex, oil viscosity, like this, the correlation. And for the laboratory data, there. Okay, so for Bex, the viscosity is matched. For Bex et al. Correlation, again, for viscosity. Okay, so in conclusion, for bubble point pressure, solution gas ratio, and oil formation volume factor, Glasso is the best. And for oil viscosity, Bex et al. Is the best. And now it's tick, use matching. Okay, so far so good. So for PVT, we are okay. The data has been matched. And now we go to the reservoir 1. Okay, we will build the reservoir 1. This is the tank 1. Go to the input tank data. Okay, I will call it tank 1. And then the temperature 250, initial reservoir pressure 4000 psig, porosity 0.25, Connaught water saturation 0.15, water compressibility is 3 times 10 to the power of -6, no gas cap, and then, yeah, no gas cap, original oil in place. I think, for example, I just assume or estimate it is 200 million stock tank barrel of oil. And then start of production January 1st, 1990. PVT definition, I will use the PVT1, the one that I have constructed. And then for the water influx, I'm quite sure I don't have aquifer, okay? Based on log data, based on seismic data, okay? Based on core data, I know that for sure there is no aquifer. So model, I select none. Rock compressibility will use from correlation. And then for the rock compaction, as it is. And then relative permeability, based on core analysis data, I know my relative permeability is like this. This is the residual or connate water saturation. This is the residual oil saturation and the residual gas saturation. This is the endpoint for water, the maximum relative permeability for water. Okay. And then for the oil, 0.8, whereas for gas, it is 0.95 here. And the exponent, 1.3, and then 1.5, and then 1. Sorry, here. Okay. All right, so for exponent, for water, 1.3, 1.5 for oil, and for gas, 1. And then I have production history, and I will copy my production history data from my spreadsheet and copy the data here. Okay, data copied, right click, paste table. Okay, so I have the time, the reservoir pressure, cumulative oil, cumulative gas, and cumulative water produced. Okay, so far so good. And let me check again for the unit for the cumulative gas produced. Wait for a while. Okay. All right, so it's already correct. And now we can plot. Okay, this is the production plot. You can see the reservoir pressure, black line with the dots, and cumulative oil production, the red line. And you can see something weird here. So previously, the reservoir pressure drops significantly, drops quickly, and then it drops, it declines, but with a smoother decline. Or here we have high decline rate of pressure, and here we have mild or moderate pressure decline. And what happened? Okay, so we need to investigate that by this material balance simulation. Okay, so we close, validate, everything okay, click done. All right, again, we don't have aquifer. And then as usual, we will perform history matching, analytical method. You can see here, the blue line is actually the result from the model. And these dots is actually the actual data. And you can see 100% it doesn't match. It is only matched here, right? At this period of time, the quality of the matching is good, but here it's totally doesn't match. It doesn't match. Okay. Although I will put aquifer, I'm sure that it will not be matched also, even though I put aquifer here. Okay. So as a reservoir engineer, we understand that this phenomena can happen if I have other source of pressure. It can be aquifer, yes, but it can also be from other reservoir. Okay, we say that previously we have quick drop, okay, significant reservoir pressure drop, but after that the reservoir pressure drop becomes milder, becomes moderate. It's because there is pressure support from outside the reservoir. Okay, maybe again, maybe it is aquifer, but most likely it's not because of aquifer. Okay, so instead of making an aquifer, all right, I will create another reservoir. Okay, maybe in reality the reservoir below this existing reservoir, maybe I have another reservoir below, or maybe I have another reservoir at above my current reservoir. Okay. But yeah, just to check, if we perform regression and then here we will regress the oil in place, what will happen if we click calculate? Yeah, MBAL recommend this big oil in place. Let's click here, click done. Yeah, MBAL can give me this, but still, again, it doesn't match. Okay, it doesn't match. Although we increase the oil in place, it still doesn't match. The blue line is from MBAL, from model, and these dots are the data. So it doesn't match. So I will make the oil in place go back to 200. Okay, history matching like this. Okay, and then I will create another reservoir. Okay, I will add tank here or here instead. So for example, I have another reservoir below my reservoir. I have another tank, another reservoir below tank 1. So the data for this reservoir, after I investigate it, for example, the data is as follows. The temperature 250, the initial reservoir pressure 4,000, and then the porosity 0.25, and then Connaught water saturation 0.15, water compressibility 3 e to the minus 6, no gas cap, original oil in place, for example, 150, and start of production, this one. So more or less, it's like tank 1, okay? And then water influx, the tank 2 also doesn't have aquifer. Raw compressibility, I will use correlation. Okay, use correlation, no compaction issue, and relative permeability, the same with the tank 1. Okay, 1.3 for the oil, residual oil saturation, endpoint, exponent, residual gas, endpoint, and then exponent. And then plot if you want to check the relative permeability. Okay, the relative permeability versus the phase saturation. The same for tank 1 and tank 2. And if you want to check relative permeability of water against the water saturation, it's like this. Relative permeability of oil against water saturation, it's like this. And for the gas, relative permeability of oil versus, versus gas saturation, and relative permeability of gas versus gas saturation. Okay, so far so good. And let's say this tank 2 is virgin. I haven't put my well to drill or to penetrate this reservoir. So there is no production from this reservoir. There is no production or injection in this tank 2. My production is only from tank 1. Okay, so like this, the condition. I will move it a little bit. Okay, so I have tank 1, and below tank 1, I have tank 2. Okay, and now I want to connect them. Okay, because here in tank 1, okay, because what I see in tank 1, okay, in tank 1, I change it from here, previous tank, because of what I see in tank 1, the tank pressure versus calculated oil production, I know there is a connection between tank 1 and tank 2. Okay, my hypothesis is like this. Firstly, I only produce from tank 1. But after that, there is cross flow from tank 2 to tank 1. Okay, again, there is cross flow from tank 2 to tank 1 so that tank 2 will support the pressure of tank 1. That's why now the pressure drop or pressure decline becomes milder, becomes moderate. Okay, the pressure decline becomes slower because of pressure support from tank 2. Okay, here we have fast reservoir pressure decline. Here we have slow reservoir pressure decline because of pressure support from tank 2. Okay, so I will connect. I will make tank 1 connected to tank 2 with what? With this one, transmissibility. Okay, between tank 1 and tank 2. Okay, this is the window for transmissibility input data. Allow flow from both direction, and I need to provide with transmissibility. And for example, I guess or I evaluate or I predict the transmissibility will be 2 reservoir barrel per day per centipoise per psi. Okay, and then for the fractional flow model, I will use tank. I will use the data available in the tank, the relative permeability, and then threshold. I will use this one, 1000 psi. Okay, what does pressure threshold mean? So pressure threshold is actually the pressure that needs to be reached before tank 2 support the tank 1. Okay, so in other words, after the reservoir pressure in tank 1 drops as much as 1000 psi, okay, then the tank 2 will be active and then support tank 2. Okay, again, tank 1, after the reservoir pressure in tank 1 drops as much as 1000 psi, then the tank 2 will be responsive, tank 2 will be activated, and it will support the pressure in tank 1. Okay, so the threshold is 1000. Okay, or we can also read here help contents, and then we can check threshold. Okay, transmissibility parameters. Now we can check pressure threshold. Okay, you can read it by yourself, but we will select this one, use threshold with unequal potential. So this option is exactly the same as use threshold with equal potentials, except for the following difference. MBAL now assumes that the initial pressure difference in the tanks was not due to hydrostatic differences, but due to an actual difference which was supported by the pressure threshold in the transmissibility. This means, this is very important, that any pressure difference calculated is simply the difference between the current tank pressure, and it does not subtract the initial pressure difference. Okay. And also, yeah, the rest you can read. But again, the pressure threshold is the pressure that is required, pressure drop that is required, so that the tank 1 or tank 2 will support the pressure to tank 1. Okay, so we need to achieve 1000 psi pressure drop, okay, or 1000 psi pressure difference between the two reservoirs. Okay, we need to achieve that. We need to reach that before one reservoir will support the other reservoir. Okay, so if I close and if we check here, you can see the pressure drop from 4,000 to 3,000. Okay, 4,000 initial pressure, and at 3,000, if I zoom out, zoom in, or replot like this, after the reservoir pressure drops from 4,000 to 3,000, the pressure decline changes. Okay, why? It's because it's because of the pressure threshold. So from here, from this observation, we can say that the pressure threshold is 1,000 because tank 1 and tank 2 have the same reservoir pressure, which is 4,000. Okay, tank 1 initial pressure 4,000, tank 2 initial pressure 4,000. So if the pressure in reservoir in tank 1 drops from 4,000 to 3,000, so the difference between tank 1 and tank 2 is 1,000 psi. That's the pressure threshold of 1,000. Okay, so that's why the transmissibility or the pressure threshold is 1,000 here. Okay, I'm sorry, it's not pressure drop, but it's pressure difference between two reservoirs. If one reservoir has difference in pressure with another reservoir, and the difference will drive the reservoir with higher pressure to flow the fluid to the reservoir with lower reservoir pressure, then that's the meaning of pressure threshold. Okay, and then production history, there is no production history in the transmissibility, so we can click validate and then click done. Okay, so this is our model. I have tank 1, I have tank 2, and they are connected with this transmissibility. Or I will move the tank 1. It's better. Okay, so tank 1 and tank 2 are connected with transmissibility. Tank 1 initial pressure is 4,000. Tank 2 initial pressure is 4,000. Okay, or maybe it is better if they are at the same level. So that's why they have the reservoir pressure, the same reservoir pressure of 4,000. Yeah, it will be better like this at the same level. Okay, so initial pressure the same, but we produce from tank 1 so that the reservoir pressure will drop. After the reservoir pressure in tank 1 drops to 3,000, then the difference between reservoir pressure in tank 1 and tank 2 is 1,000 psi. Here we have 3,000 because of production. Here we have 4,000 because there is no production here. So the reservoir pressure is still initial. Okay, because of the difference of 1,000 psi, tank 2 will give the fluid to the tank 1 because they are connected. Okay, yeah, let's say transmissibility here is the leaky fault. Okay, we have, for example, fault here, but it's not sealing fault, it's leaky fault. So tank 2 will give some fluid to tank 1 so that pressure in tank 1 will be supported by this tank 2. Okay, that's why if we check the pressure in tank 1, plot the pressure, the reservoir pressure decline becomes slower because of support from tank 2. Okay, so I need to explain the story quite comprehensively so that you get a clear picture about what transmissibility is, what is the connection between two reservoirs. Okay, so from here we go to history matching, and you see the red line is model without transmissibility. So clearly the red line doesn't match. Without transmissibility, the model doesn't match. Okay, the model is wrong. But with transmissibility, now I have blue line. And you can see blue line gives better match, although it still doesn't match. Okay, so now my hypothesis is right. Blue line is almost correct. So they are connected between tank 1 and tank 2. They have transmissibility between them. So what I need to do now is to regress. Regression. Okay, I need to regress because I'm still not sure about the transmissibility and about oil in place. Okay, I'm still not sure about what the oil in place. So I will keep the 200. I will keep the 200. Let's say I'm sure. And then I will regress for the tank 2 and the transmissibility. Okay, so I will calculate and the MBAL will estimate. So MBAL thinks that tank 2 should be 333 and the transmissibility should be 2.94 in order to achieve the best match. Okay, let me check. I click this one. So now the oil in place in tank 2 is 333 and the transmissibility should be 2.94. So let's check, click done. And you can see we achieve perfect match. Okay, so now I have the correct oil in place for my tank 1 and tank 2. And also I have the correct transmissibility between the two reservoirs. Okay, so that's the importance of simple reservoir simulation with this software, with material balance calculation. Now I'm quite sure, quite certain about the oil in place in tank 1, in tank 2, and I also know the transmissibility between the two reservoirs. Okay, that's the significance, that's the importance of this simulation. Okay, and this is still with analytical method. We need to check the graphical method. Okay, the method Haflena Odeh. We will match the tank 1. Okay, it is difficult to analyze with graphical method because usually in graphical method we only consider one reservoir. So that's why we see blank here and then change to other method, right? Graphical method cannot express the transmissibility between two reservoirs. Yeah, it is better. So the graphical method can capture only here. And you can see here is actually the period where the reservoir tank 1 produces alone without support from tank 2. And here is the period where the tank 2 already supports the tank 1. Okay, so the graphical method is not very good to analyze connectivity or transmissibility between two reservoirs. And also let's check the next method. Okay. Yeah, it still also doesn't match. Yeah, very limited. So if we have two reservoirs and they have transmissibility, the best method should be analytical method like this. Okay. And then we can check the graphical method. Oh no, sorry. The energy plot for tank one. This is the drive mechanism analysis. So the main drive mechanism is fluid expansion, of course, because we don't have gas cap, we don't have aquifer. So the main drive mechanism is fluid expansion and also pore volume compressibility. Okay, and we click next tank 2, because we don't have production data in tank 2, so it is blank. Okay, so we cannot analyze the drive mechanism in tank 2. Unfortunately, we only can analyze the tank 1 because it has production history. Okay, so click finish, and then this is for all analysis. Again, our main method is analytical method, and click finish. Now check the run simulation, calculate. Okay, plot, check the tank 1 production history or tank pressure like this. Now we compare with the simulation, tank pressure, right? Perfectly match. Yeah, we can still make the match better, but I think it's not very necessary because from here we can see that it is almost matched. Okay, and then now we can generate the average oil rate like this. And if we want to show the recovery factor, then it is like this. Okay, so production from 1990 to 2003, we still can only reach recovery factor of 7.3966 or 7.4%. Okay. Yeah, you can also plot others. If you want to show the average oil rate, average gas rate, average water rate, there is no water. Okay. And then the reservoir voidage. And then what can we show from transmissibility? Yeah, this is the flow transmissibility. So 0 previously, because still the pressure threshold hasn't been reached. So there is no flow from tank 2 to tank 1. That's why it's 0. But after that, there is flow. That's why here we have negative value showing the support from tank 2 to tank 1. Okay, previously 0. Previously there is no flow. That's what we can plot in the transmissibility. Very interesting. Okay, click done. And we will not do prediction here. So the main thing that we learned in this video is how to simulate the transmissibility or connectivity between two reservoirs. So we can recap. In this video, we construct a reservoir model. It has production history, and we know from the production history there is something weird about this, because here we have fast reservoir pressure drop, but after that the pressure drop becomes slower. So we ask ourselves, what happened? Is there any aquifer, or is there another reservoir that is supporting our reservoir or our reservoir? We know for sure there is no aquifer based on log, based on seismic, based on core, there is no log, there is no aquifer. So the only reason is that we have pressure support coming from the outside of our reservoir. So we analyze and we think that there is another reservoir that is connected somehow with our tank one. And for example, there is leaky fault or there is connection between tank one and another reservoir. So we create transmissibility to represent the connection between tank one and this tank two. Okay. And we know that we still haven't produced any fluid from tank two. So we create the model for tank two, but there is no production history. And then we connect tank one connected with tank two through this transmissibility, and we perform history matching, okay, in the tank one, and we do regression to get the correct oil in place of tank two and transmissibility of tank two, or I'm sorry, or transmissibility between two reservoirs. And then we obtain perfect match and we are satisfied. Okay, so that's the whole story. I hope you understand and see you again in the next learning for this reservoir simulation. Thank you.